Chapter 21 Chemistry Theory Video 3. So we are going to discuss how to find the pH of strong acid. Now we know that strong acids are completely ionized in solution. And also we discuss about monobasic acids. Monobasic acids mean the acids which have like HNO3O HCl, which has only one hydrogen atom per molecule. So if we take the concentration of the hydrogen ions, it would be approximately similar to the concentration of the acid. So with that assumption, we find the concentration of or the pH value of a strong acid. So what we need to understand is we don't consider the pH of pH of water here, because we don't take the H plus ion concentration of water here, because we assume that to be very very less in comparison to the H plus ion concentration of the acid. So again what we do is we follow the same equation and same formula, that is pH value negative logarithm to the base 10 of H plus ion concentration. So if they give you hydrogen ion concentration of solution whose pH is 10.5, then what we know the equation, pH is equal to negative logarithm of H plus ion concentration to the base 10. So then H plus ion concentration is equal to 10 to the power negative pH. Then we get 10 to the power negative 10.5, which is going to be 3.16 into 10 to the power negative 11. So try this several times, so until you are completely familiar with the way how you do it. Then if you are completely okay, you can get it done. So then write down a note on this. The pH of a strong acid can be calculated by taking the assumption that the H plus ion concentration of it is equal to the concentration of the acid. We do not consider the H plus ion concentration of water for this. I would suggest that you write down this worked example 2 for you to understand, and then try many different questions. So calculate the pH of strong bases. So in strong bases, we know that in strong bases we know that it is H plus ions is coming from water. So we know that the ionic product of water is given by Kw H plus into OH minus ions. So then we can find out if we know the Kw and H plus ion concentration, we can find out the hydroxide ion concentration. So that is something that we need to know. Then if you take a strong base such as sodium hydroxide, it is completely ionized. So that is it is the concentration of hydroxide ions would be approximately similar to the concentration of sodium hydroxide. So as a result, we have the OH, we need the OH minus ion concentration to find out the OH minus ion concentration needs to be found out. So now we know that it is more or less similar to the concentration of the base, strong base. Then to find out the pH of the solution, we need not only the concentration of OH minus ions, we need the equilibrium expression for ionization of water, that is Kw, then value of Kw, and then we know that it is defined by the H plus ion concentration is equal to Kw upon OH, and then using this equation we can figure out the concentration of or the pH value of a strong base. So the worked example will explain how to do this. So if they give you calculate the pH of a solution of sodium hydroxide of concentration 0.05 mole per cubic decimeter, then they will give you Kw is equal to 1 into 10 to the power negative 14 mole square dm minus 6. Then the first thing what we need to do is we have the equilibrium expression H plus is equal to Kw upon OH ion concentration. So we have the Kw value 1 into 10 to the power minus 14. We realize that because it's a strong base, it is going to be the H plus ion concentration, the OH minus ion concentration is equal to the concentration of the weak, strong base. So that is 0.05. Then when you find the solution, it will be 2 into 10 to the power minus 13 mole per cubic decimeter, that is H plus ion concentration. So now you need to find the pH of this. The pH is negative logarithm of H plus ion concentration to the base 10. You use the value 2 into 10 to the power minus 13, you get 12.7. Right, there is a quick way to do this, just that is to find the negative logarithm of OH minus ion concentration directly and then subtract it from 14. But I would suggest that you know the longer method, because it will not confuse you in any format. So once you have understood all, please do question number 4. But before that, write down an equation, write down a note. To find the pH of a strong base, we go to the assumption that all of the H plus ions that would be coming from water. Also, we assume that all of the base molecules would have dissociated, within brackets ionized. We use the equation H plus ion equals Kw upon OH minus ion concentration. H plus ion concentration is equal to Kw upon OH minus ion concentration, to find the H plus ion concentration, and from that we use the H plus ion concentration to calculate the pH. If you understood, please do question number 4. If you did not understand, please ask questions. Now we are coming to discuss about weak acids. So in weak acids, we have to use something called the acid dissociation constant, Ka. Now the reason why we need such a acid dissociation constant is because we know that not all the molecules would dissociate or would ionize in weak acids, and it is going to be the same for weak bases as well. Now if you take ethanoic acid, there is an equilibrium that is going to be established when CH3COOH joins with water to produce hydroxonium ion and CH3COO minus ion. We generally write it as ethanoic acid dissociating into H plus and CH3COO minus. So then the equilibrium expression is going to be H plus into the products over reactants. This is something that you know. Ka is referred to as the acid dissociation constant, which is going to be H plus into CH3COO minus divided by CH3COOH. So this for the ethanoic acid, this acid dissociation constant is going to be 1.74 into 10 to the power minus 5 mole per cubic decimeter. It is also found in the same way as Kc. And for a monobasic acid, the units are going to be mole per cubic decimeter, because only one is going to be left out, H plus ion, H plus. Now as you can see here, at the top you would have two concentrations, H plus ion concentration into CH3COO minus concentration, that is the ethanoate ion concentration, divided by the ethanoic acid concentration. So one concentration at the top to bottom concentration would get cancelled out, therefore one concentration is going to remain. So that is the reason why for a monobasic acid, the Ka is going to have the unit moles per cubic decimeter. So for a monobasic acid HA, we know the equation. HA is is going to dissociate, or the equilibrium is going to be reached at H plus aqueous plus A minus aqueous. Therefore, we can develop a general equilibrium expression for a monobasic acid, that is Ka equals H plus into A minus this molar concentrations divided by Ha concentration. So Ka indicate the extent of dissociation of the acid. So this is not going to be the same for all the all the acids. It is going to be different from one acid to another. So if there is a high value for Ka, for example, if you have 40 moles per cubic decimeters, then that means the position of equilibrium is going to lie more to the right. So that means the acid is almost completely ionized. So that is going to be for a stronger acid. Then low value for Ka means the equilibrium position is going to lie to the left. That is now if you consider if this is the end point, so this is the acid at this point and this is the products. So what happens is, if there is a high value for Ka, then the equilibrium lies at the right, means all of this would have dissociated. So more acids have dissociated if the Ka value is high. Then we say that the equilibrium position is more to the right. So it is almost completely ionized. Then if it has a low value, then what happens is it is going to lie somewhere here. So as a result, it is shifted to the left. That means only few acid molecules have dissociated. I hope that makes sense to you. So that means there would be more Ha molecules and few H plus ions, H plus and A minus ions. For many weak acids, the Ka values are very low. So because of that, we use pKa values to compare their strengths. pKa values are taken by obtaining the negative logarithm of the Ka value to the base 10. So that will give us something similar to something that we take in comparison to pH value, something like that. We get a pKa value because these values that we have cannot be compared without confusing ourselves. So as a result, we use the pKa values. For nitric acid, the pKa value is negative 1.4, and when it comes to water, it is negative 14. You can see that they have the lesser the water is, the water dissociates only very slightly. So as a result, you can see that it has a very low pKa value. Then ethanoic acid, benzoic acid, the pKa value does not show a pattern until up to this point. Until 9.89, you can see that it is increasing. Then beyond that, it is all negative. So these are for ions: hydrogen carbonate ion and hydrogen silicate ion, water. Then when it comes to acids, you can see up until 9.89 it is increasing, the value is increasing. There is a general trend there, but don't try to find the trend in the other three, but because they are not for acids but they are for ions and water. So if there is a if there is a question given using pKa values, you know how to convert that into Ka by using the same equation. pKa is equal to negative logarithm of Ka value to the base 10. I hope that makes sense to you. And also remember the P value, the symbol P in relation to acids and means, acid and bases mean the negative logarithm. So pH is negative logarithm of H plus ion concentration. Then pKa means negative logarithm to the base 10 of Ka. I hope that makes sense. Let's write down a note on this. Weak acids using the acid dissociation constant. Weak acids and weak bases do not dissociate fully. Example, CH3COOH aqueous plus H2O liquid gives H3O plus aqueous, that is a hydroxonium ion, plus CH3COO minus aqueous, which is generally written as CH3COOH aqueous, reversible sign, H plus ion aqueous plus CH3COO minus aqueous. Then equilibrium expression Ka equals H plus ion concentration square brackets CH3COO minus ion concentration divided by CH3COOH concentration. Ka is acid dissociation constant, and for ethanoic acid it has a value of 1.74 into 10 to the power negative 5 mole per cubic decimeter. General formula: HA aqueous, reversible sign, H plus aqueous plus A minus aqueous. Therefore, Ka equals H plus A minus H plus ion concentration into A minus ion concentration divided by HA concentration. For monobasic acids, Ka would have mole per cubic decimeter units. Leave a line, put a star and write down. If an acid has a high Ka value, for example 40 mole per cubic decimeter, the position of equilibrium lies to the right. Acid is almost completely ionized. Low value for Ka, for example 1 into 10 to the power minus 4 mole per cubic decimeter. The acid is only slightly ionized and exists mostly as Ha molecules. When the Ka values are very low, we use pKa values to compare their strengths. pKa equals negative logarithm of Ka to the base 10. I hope this makes sense to you. If it does not, please ask questions. Do question number 5 once you have done it.